Okay, let's have a look at the pH for a dibasic or a diprotic acid, as it's something called. Now, you might have expected diprotic acids like sulfuric acid to be twice as strong as monoprotic acids. So you always kind of intuitively felt that H2SO4 was stronger than HCl. Okay? But it isn't actually the case. If we take sulfuric acid, we know what the molecule looks like. You can practice drawing it if you want. It does dissociate, and this first dissociation, we can consider this first dissociation to go to completion. We typically do. Okay? Then we have a second dissociation, which is losing the second proton, and this is the dissociation that's considered to be, well, quite significantly to the left-hand side. It definitely doesn't go to completion. It's a weak acid, so we can consider this hydrogen sulfate ion to be a weak acid. Okay, so the top one goes to completion, and the second one is a partial dissociation. What happens is, because there's lots of these present after the first dissociation, then this second dissociation is suppressed. It's kept to this side. If we increase by Le Chatelier's principle, we increase the concentration of H3O+, then it forces this equilibrium to this side. So the second ionization, we can say, is suppressed by the first, and it has a Ka. Now remember, Ka exists for weak acids, so that's the Ka of this hydrogen sulfate ion. Okay? The pH of a 0.1 molar solution of sulfuric acid is 0.98. The pH of a 0.1 molar solution of hydrochloric acid is 1. So there's not that big a difference, is there? Now we have to be able to do this calculation. So let's take an example. 0.5 molar sulfuric acid. If it were fully ionized, if this is the hypothetical case, you would expect, well, the hydrogen ion concentration would be 2 times 0.5, because it's 0.5 molar, so that means you've got 2 moles of hydrogen ions per mole of sulfuric acid. So you'd expect the concentration of hydrogen ions to be 1. So the pH, you do your little logarithm, and the pH should be 0, but it's not. So let's have a look at the calculations involved. The first dissociation is complete, as given there, and this will provide 0.5 moles per decimeter cubed of the hydrogen ions, won't it? Okay, this is complete. If we start with 0.5 mole per decimeter cubed of this, then we're going to get 0.5 mole per decimeter cubed of this and of this. Great. The second ionization is not complete. So this ion does not completely dissociate. There's a Ka for this second dissociation. You'll get some extra hydrogen ions, so the pH will drop slightly, but we have to use a weak acid calculation to work out what the pH is going to be. So let's look at this specifically and try and work out the pH. There's the full equation for the first dissociation, and that dissociation is complete. So 0.5 moles per decimeter cubed sulfuric acid gives me 0.5 and 0.5 moles per decimeter cubed of the oxonium ion and the hydrogen sulfate ion. Great. What's the Ka expression for this second dissociation? The dissociation is not complete here, so we have to write a Ka expression. Well, 0.5 moles per decimeter cubed of this, in this case, we've got to use a little bit of algebra to work this out. We say that 0.5 dissociates, we get X of the sulfate ions, but we get, as well as X from this dissociation, we've got 0.5 of the oxonium ions from the first dissociation. So my total oxonium ion concentration now is 0.5 plus x. And if x has reacted, in this case, then we've got 0.5 minus x of the hydrogen sulfate ions left over. Okay. Now, let's think about my expression for Ka. We've got Ka is going to be these concentrations divided by this concentration. Remember, the water doesn't figure, does it? So Ka is going to be, we're going to use the figure 1.20 times 10 to the minus 2 for Ka, and it's going to be the concentration of the oxonium ions times the concentration of the sulfate ions divided by the concentration of the hydrogen sulfate ions. Okay? Now, the mathematicians amongst you will realize that that's a quadratic, isn't it? So, have a go at solving that quadratic equation. That'll take you a little while. I'm not going to do it here. I'm not here to teach you maths. So you'll find that x, or one of the values for x, the positive value, will be 0.0115. That's the extra hydrogen ion concentration. So the total concentration of the hydrogen ions will be 0.5 plus that. Okay, now we've got the hydrogen ion concentration. We can work out the pH. pH is minus log to the base 10. I'll let you work this out. Put the numbers in. And you get a pH of 0.29. Okay, remember, if it had been fully ionized, it would have been a pH of 0. We've got a pH of 0.29.